Is that better?
Okay, perfect. We can see presentation view. So please, screen is yours.
Okay, great. Greetings, my name is Artur Kostera, and I'm going to talk about my expert system for analyzing city images using CNN with a self-attention model. As you can see in the picture shown, under the expected conditions, working with presented system should start with a patient wishing to be diagnosed by a doctor. This doctor examines the patient using a CT scanner. Then he sends the received result of the examination to the database of the given system, after which it is launched. Comparing the received data with a database of correctly categorized similar images, the system should, after a moment of calculation, determine whether the patient is healthy or not and display the accuracy of its decision. The application of artificial intelligence is mostly an expert system. Such a system is created to support an expert and is created based on his/her knowledge. In general, a classic expert system is defined as a rule-based model, but it can be also modeled with classifiers. It can be justified through non-numerical data, and an example of which is graphic data. Moreover, attention should be paid to the issue of practical application, because the use of a neural network as the main engine of the expert system allows for returning the classification results, which is understood as an additional opinion. Neural networks are mathematical models inspired by the functioning of the human brain that receive various data and then process them. The main idea of a neural network can be described by defining the operation of a single neuron, because the neuron is a set of such units arranged in columns called layers. Assume that a given neuron possesses one of the values obtained from another neuron via a connecting synapse. We describe such a synapse by a weight value. We then multiply the value received from another neuron with the weight of the synapse through which it passed. The result is called using, for example, the ReLU function, so that its value does not cause problems, which can be generated in the case of very large values, among other things. If there are more neurons in the previous layer, we sum the results of the products of the obtained values with the weights of individual synapses. Then, only when we have already obtained the combined results, we scale the value using, for example, the previously mentioned function. Convolutional neural networks is a newer network architecture that allows processing and analyzing images. It is a type of deep learning model that is specifically designed for processing spatial data, such as images. CNN is particularly effective at analyzing patterns in multidimensional data, making it an ideal tool for image recognition, classification, segmentation, or object detection tasks. Its architecture is also built on layers. The first type of layer that is used in the convolution one, which is the convolution one, which is based on modifying the image to exact features. The layer has a set of weights called a kernel or filter. Usually, such a kernel can cover only a small part of the entire image at a time. The filter starts from the upper left corner on the image, moves one pixel at a time to eventually cover the entire image. Covering each pixel involves modifying its value, which is accomplished by analyzing its neighbors. That is to say, the previously mentioned neighboring pixels. Modification and the meaning of each variable are described in the slide shown. The second type is the pooling layer, whose task is to minimize the image size while maintaining the most important features of objects in the images. The idea of action can be described as selecting a specific value at a given position relative to the neighborhood. As an example, we take the size of the analyzed neighborhood as 2 by 2 Then the pooling layer select the value and that the pooling function indicates. The most commonly used values are maximum, minimum, or average. After selecting a given value, the layer analyzes the next position in the image. The third type of layer is the fully connected layer, which is composed of neurons described uh, earlier. For the expert system being built, a neural network model consisting of 14 layers was built. The input layer accepts images of dimension 224 by 224. Then the image from the input layer is passed to the convolution layer, which has 32 filters of size 3 by 3 to focus on extracting relevant elements. This layer uses the ReLU function, that is rectified linear unit. The function used is based on leaving positive values and replacing negative values with 0. The next layer is pooling with a maximum function which focus on removing data with the smallest values. Thanks to this process, the amount of calculation that the program still needs to perform is once again reduced. In the next steps, a set of layers is added 3 times, convolution and poolings. The difference is the number of filters in the convolution layers, which are increased to 64, 128, and 256. The return result from the fourth pooling layers is transferred to the attention module, whose task is to mark individual image elements with weights that will allow the identification of important features. The resulting tensor is flattened to pass it to dense layers. As you can see, the network model has 3 fully connected layers of 256, 128, and 2 neurons. And the last layer has only 2 neurons due to binary classification, that is returning values of 0 or 1, meaning the patient is sick or the patient is healthy, respectively. The first 2 dense layers use the ReLU function as an activation function, and the last one use the softlock function, which, based on the information received from the previous layers, determine probability values regarding the class of the process image. Training involves modifying weights in the entire model, including filter values in convolution layers. For this purpose, the ADAM algorithm is used, which is based on the modification of values by determining statistical values such as moments of a selected order. To check the performance of the classifier, the classification accuracy as well as the loss value are verified. This second metric is defined depending on the selected problem. For the binary problem, we use the cross-entropy function. However, in the context of analyzing a large number of samples, here batches, second function takes presented form. The entire process should be repeated until the network achieves satisfactory effectiveness. The learning process is performed for a specified number of epochs or until previously set loss function values or accuracy are obtained. The attention module is an element of the neural network that allows you to add weights to all values in the processed sample. For this purpose, the weights will have values in the range of 0 to 1 and will be interpreted as the significance of a given value. To describe this module, it should be assumed that the weight values will be marked with a presented matrix. The first step is to determine the attention score relatively to the matrix and the weights and rescaling by the softmax function. A weight and sum is then performed along the axis elements of the last function shown. The test used a database of computer tomography images from COVID and healthy patients. The data set consisted of 1,255 scans of patients which confirmed coronavirus and 1,229 scans of healthy patients. The set was randomly divided in a 70-30 ratio, where 70% of the data was used for training purpose and the remaining 30% for classifier validation. Now on display is a confusion matrix that was generated for the trained model on the validation set. Lines marked as true label determine whether a given photo show a scan of person suffering from COVID or not. In turn, columns marked as predicted label indicates how the system assessed a given photo. Combining these two pieces of information, we know that the number in the first field, that is the field that belongs to both the COVID row and the column with the same name, means cases in which the system received a photo of a sick person and diagnosed the patient that way. The same only for photos of healthy patient applies to the number containing in the field belonging to the non-COVID row and the columns of the same name. The remaining two places are the number of situations when the system made a mistake. Additionally, we also see that the intensity of the blue color means how often the model made a given decision. Based on the numbers and color intensity, we see that in most cases the model responded correctly. By comparing the number of correct answers with incorrect ones, we obtain a level of accuracy of 94%. As you can see from the results the system has achieved, it could centrally be used as a second opinion for a doctor. The system is able to draw attention to details that a doctor might have overlooked. As part of project development opportunities, I can extend expert system architecture to an end-to-end model that could be used in a more flexible way. The next natural move in developing the project would be to expand the system's capabilities so that it can recognize more diseases. If over the years the system collected a large enough amount of data needed to identify a disease, one could think about solutions that do not require a doctor. And that will be all from my presentation. Thank you for your attention.